And good. All right. So, guys, today what we're going to do is we're going to wrap, holy smokes, we're going to wrap up the unit. We're going to wrap up the year, last day of lecture, right, by talking about two things called Avogadro's principle and what's called the ideal gas law. And yes, this is the same Avogadro that came up with the number 6.02 times 10 to the 23rd. The thing that we didn't talk about is when Avogadro came up with his magic number, he was actually studying gases. And as he was studying gases and trying to count gas molecules, he came up with a really crazy observation that I'm going to share with you in a minute that's called Avogadro's principle. Now, guys, here's the trick, and I think I shared this with you. We are spending 2 total days lecturing about gases, right? We're going over this briefly. We're introducing some ideas, Boyle's and Charles' law, ideal gases, that kind of stuff. But guys, when you come back for AP next year, this stuff gets big and difficult. So now it's just sort of an overview. We'll talk about it briefly. We're going to do a little bit of math and the day's going to be over. Okay, so with that said, gang, don't write down anything that comes up on this first slide, this first page of slides, but we're going to get you thinking about Avogadro's principle. So you do want to write this down in your notes. So guys, we're going to start by helping you understand what is crazy about Avogadro's principle. Avogadro's principle doesn't make sense until you understand it. Okay, so it goes like this. Guys, don't write this down. Just play along at home. So guys, 30-gallon trash can. Okay, that's how big that thing is. Its volume is 30 gallons. Now, I'm going to ask for guesses. These are not rhetorical questions. But guys, the question is this. I'm going to have you estimate how many objects it will take to fill this trash can. And frankly, I do know the answers. But I'm going to give you the opportunity to guess. So the question is, how many of these, and I'll show you these in a minute, does it take to fill this trash can? So guys, these number 1 are tennis balls. And I probably should have one to show you, but you know, they're about that big. So guys, the question is, how many tennis balls would it take to fill the trash can? What do you think? You're a tennis player. Come on. 150? Other guesses? Would anyone go lower? This is like The Price is Right. Would anyone go lower than 150? More than 150? Surprisingly, you're not even close. Well, you're kind of close. Guys, so no one's going lower than 150, but can you imagine that trash can full of tennis balls? Can you picture that thing all stacked full of tennis balls? And it turns out that it's not 150, it's actually right below 400. Guys, it takes a bunch of tennis balls to fill, and you can picture it, right? All of these little tennis balls stacked up inside, fill that thing with tennis balls. It's just short of 400 tennis balls. But you get the picture, right? Okay, so now let's try this. Same question, different ball. What about volleyballs? So guys, volleyballs are about so big around. The question is the same. How many volleyballs does it take to fill the trash can? It's actually less than 10. It's actually 7. Guys, and understand that's so, just so they're to the top and not overflowing. But guys, can you picture 7 volleyballs inside of here? Why does it take so much fewer volleyballs? One, they're bigger, right? But can you also picture that there's going to be a lot more empty space around them because they can't pack as tight? Okay, well, all of that to say, and none of you were surprised, right? We knew that if it was 400 tennis balls, I pray that none of you was thinking it's going to be 500 volleyballs, right? Because at least you understand the concept that it takes more small things to fill a space than it does big things. You guys comfortable with the idea? Okay, so guys, we are going to make that our functional hypothesis, and don't write this down, but make sure that you can agree with this mentally. So guys, this is our bold statement, that it takes more small things to fill a space than it does big things. You guys groovy with that idea? All right, so now guys, let's talk about chemistry. So here's what I've got. I got 2 balloons, And before school today, I filled these. I've actually got gas tanks over in the other room. Unfortunately, this one's leaking a little bit, so you're just going to have to trust me here. These used to be the same size. Well, are they still close? Green guy's a little smaller, isn't he? No? All right. So for this to make sense, guys, you've got to understand that these should be the same size, and I promise you they were about 20 minutes ago. So guys, with that said, let's remind ourselves of our hypothesis. Here's what we've said. It takes more small things to fill a space than big things. You good? All right. So now, guys, let's turn our attention away from tennis balls and away from volleyballs, and let's talk about molecules. So guys, the drill goes like this. This is hydrogen. It's H2. It's diatomic. This is C3H8, which is actually propane. So when I filled this guy, I just have a little propane tank with one of those helium thingies on it and filled it up. And so anyway, so guys, this guy's got hydrogen in it, and this guy's got propane in it. And so guys, this balloon on your left is full of these little dudes. See how this is kind of connecting to what we just talked about? This balloon on the left has got a bunch of these little dudes in it, and this balloon on the right has got a bunch of big dudes in it. Now here's the question. How many dudes are there? Are there more hydrogen molecules in here, or are there more propane molecules in the yellow guy? Why would there be more hydrogen molecules in the green guy? Because the hydrogens are smaller, right? In the same way that it takes more tennis balls than volleyballs to fill the trash can, it takes more hydrogen molecules than it does propane molecules to fill the same space, because the hydrogens are smaller. Does that make sense? Do you get the idea? Because it's completely wrong. Guys, it turns out that that is not true. That there are not more hydrogens in here than there are propanes in here. It turns out that there's exactly the same number of these in here as there are these in here. So guys, when we're talking about balls, it works. More small things to fill a space. But when we're talking about gas molecules, the rules change. It doesn't take more small things to fill the space. It takes exactly the same number. Why? And guys, I don't ask that rhetorically. Why? Why does it take the same number of hydrogens that are small to fill the balloon as it does butanes that are big? Yeah.
It's like they're not touching, they're moving around, so to get the same space filled and they're moving around.
Brilliant. Guys, did you hear what Robert said? Can I show you what I think he's talking about? Here's the problem. Guys, this is the misconception. So this beaker on your left has got airsoft BBs in it. Guys, these airsoft pellets represent the hydrogen molecules. Over here in this one, we've got ping pong balls, and they're just about representative in terms of their size differences. If a hydrogen molecule was the size of an airsoft pellet, then a propane molecule is about the size of a ping pong ball. And so guys, you can clearly see which contains more, airsoft pellets or ping pong balls. The airsoft pellets, right? So if this is really the way gases behaved, it would take more small hydrogens than big propanes. So now, Robert, now that we can all look at this together, what's wrong with this picture? That's brilliant. Yeah, this is what solids look like. Guys, solids are locked into fixed positions. So what do we need to do if we want to turn this into what a gas looks like? Spread them out. And so guys, this is actually pretty close to representative. This is more like how many molecules would be in this space if it were a gas. It's not thousands and it's not dozens, it's about 2. So if we could reach inside of that balloon and if we could grab a sample of gas and expand it proportionally, there would be about 2 molecules of hydrogen and about 2 molecules of propane. But guys, what are these molecules doing? moving around at hundreds of miles an hour. So the idea here is that these gases don't fill the space because they fill the space. These gases fill the space because they're moving, and because they're all spread out, this is really annoying, and because they're all spread out and moving really fast, it doesn't matter if they're small or if they're big, there will be the same number of them in a given volume because they don't fill the space because of their size, they fill the space because of their movement. And as a result, guys, there's exactly the same number of hydrogens as propanes in those balloons. Do you get the idea? Okay, so guys, that is what is called Avogadro's hypothesis. You've already written it down. Now let me define it for you. So guys, Avogadro's hypothesis is this, and this is what you want to write down. Two similar gases, gas samples, will contain the same number of molecules. That's the weird part. Seems logical that it should be more small things than big things, but it's not, and now you know why. But guys, two similar gas samples will contain the same number of molecules because the particles, as Robert said, are not in contact, but they're small, rapidly moving objects. And because they're moving so rapidly, their sizes really don't matter. They fill the space because of their motion. You guys like the ping pong balls? I made that up myself. I should be a teacher. I know. So guys, I'll give you a second to write this down, and then we're going to talk about what it means to be similar. When we're done talking about what it means to be similar, then we're going to describe this mathematically, and then once we're done describing this mathematically, we're going to solve two problems, and we're done for the day. It's about 7 more minutes. You guys all caught up? Not yet? I'll wait. While we're waiting, can I just tell you right now? Well, never mind. I'll tell you later. I'll tell you later. What is that? The funny thing is I think you're right. Yeah, I think it's like one of those fish with the dangly thing, and that's weird. Are you guys, oh yeah.
I was just going to ask a question. So, like, it's moving so rapidly?
Yeah.
Keeps it, I guess, in shape or whatever?
Yeah, that's a great way to think of it, yes.
Okay, so,
yeah.
So instead of just beings that are kind of holding it, it's just like...
Yeah, and so what we call that is pressure. So you can picture these molecules doing this, pushing against the balloon, and that's what creates pressure. Yeah, that's exactly right. Yep. You guys good? Okay, so gang, let's talk about this then. What does it mean to be similar? So guys, let's take again our two gas samples. Ready? And you should be able to think through this, but let's see how you do. What is the same about these two balloons? What is the same about these two gas samples that guarantees they contain the same number of molecules? They're the same, well, yeah, so they both contain hydrogens, but that's not it. What is the same about these gas samples? They have the same, will you give that to me, the same size? I know, green guy shrunk a little, but guys, understand if their sizes aren't the same, they won't contain the same number of molecules. So they gotta have the same size. What else is the same about these two gas samples? Yeah. Okay, so they're in similar containers with similar sizes. Think a little more abstractly. What else is true of these gas samples? Say it again. Yeah, they have the same pressure. How do we know their pressures are the same? Because they're being squeezed by the same atmospheres, right? This is experiencing atmospheric pressure, so is this, and because they're in the same atmosphere, their pressures are the same. There's one more. What else is the same? What temperature are both of them? room temperature, and they're in the same rooms, so their temperatures are the same. So guys, you want to write those down with me. When we say similar, we mean similar pressure, as Brooklyn said, similar temperature, and similar volumes. So guys, those have got to be the same. In order for this rule to hold true, that they have the same number of molecules, they've got to have the same temperature, the same pressure, and the same volume. Now guys, can I let you in on the secret? So, hydrogen, what's wrong? Hydrogen's lighter than air. It actually floats. This doesn't contain propane either because it could explode. So actually I just blew these up with my mouth about 10 minutes before class started. It really doesn't contain hydrogen or propane because that would be really dangerous. But you understand the concept, so it worked. Right. All right. That'd be a good way to end the year, right? With an explosion. Okay. So guys, you good on this idea of similar temperature, similar pressure, similar volumes, similar number of molecules? Okay. So guys, with this understood conceptually, we now need to talk about it mathematically. Now guys, understand that this is so important that my AP students 2 years ago actually printed me a hat with this equation. I've never worn this hat. I have no intention of ever wearing this hat because I am not that teacher. But the equation is this. It is lovingly called PIV-NERT. Well, read it. It's PV is equal to nRT. We call it PIV-NERT. All right, so guys, let's pick this thing apart. Ready? This is pretty cool if you can do that. You don't need to do this with me, but just watch. So guys, PIV-NERT, which is the ideal gas equation, describes Avogadro's principle. So guys, watch really close. What is the P in PIV-NERT? Pressure. So right there, we've taken care of pressure. What is the V in PIV-NERT? Volume. What is the N in PIV-NERT? This is new. N is number of moles. That is actually the abbreviation that Avogadro gave to the mole. So that's the number of molecules because we count molecules in the units moles. And then guys, R we'll talk about in a minute. What's T? Temperature. See guys, we have covered Avogadro's principle in equation form. That's all PIV-NERT is the mathematical representation of the PIV-NERT of the Avogadro's principle concept. So now let's define terms. Guys, you know that P is pressure, but it has to be in kPa. You know that V is volume, but it has to be in liters. Your units count. You now know that N is number of moles in moles. Now guys, what about R? Well, this was kind of the brilliance of Avogadro's work. What he did was this. He measured the pressure, measured the volume, measured the number of moles, and measured the temperature of a bunch of gases. And he was trying to work out the math of how these things relate. And it turns out this wasn't true. Pressure times volume was not equal to the number of moles times temperature. But it turns out that their ratios were always the same, and the number of moles times temperature was always about 8 times smaller than the pressure times the volume. And so what he did is he stuck a constant in here called R. It's called the universal gas constant. And guys, it is a constant. Its value will be given to you on the AP test, on the unit test. But guys, the value for R is 8.31. Sorry, this is sort of trailing. Here, I can make it bigger. The value for R is 8.31, and the units are liters, kilopascals per mole Kelvin. Well, but guys, it makes sense, right? If you solve this equation for R, you've got liters and kilopascals, and then the denominator dividing by N and T would be moles in temperature in Kelvin. Makes sense. And so guys, this R value is simply the value that is necessary to make the right side of the equation equal to the left side of the equation, and it doesn't change. By the way, guys, in lab on Tuesday, you're going to go collect some gas samples, measure the pressure, the volume, the number of moles, and the temperature, and you're going to solve for R. So now let's talk about T. T is temperature, and it has to be in Kelvin. Would that have been more clear and meaningful if I'd been wearing the hat? That's good. I can't. I don't even know if it fits. I can't. I can't. I haven't up and I can't. I can't. You're right, I can. I just won't. All right. I don't know. No, I don't want to be that person. For the same reason that I didn't dress up as a mole when we learned about moles, I can't. And so I don't know how Facebook found out that I'm a chemistry teacher, but you know how you get these targeted ads on Facebook and Instagram and other places? Most of the targeted ads that I get are like stupid chemistry teacher t-shirts that say things like, I'm a chemistry teacher, when I talk you should be taking notes, and things like that. And I'm like, good heavens, am I really that sad of a person? But I can't go there. All right, so guys, you good on this? So here's what we're going to do. We're going to solve this. We're going to solve a couple of these. And the math is really straightforward. We've got PivNert, which is 4 variables and 1 constant, R. So R will always be constant. Of those 4 variables, you'll be given 3. You solve for the one you're not given. Not bad, right? So guys, let's do one of these together. It reads like this. If you'd like a second to write it down, we can do that. But it says, what volume does 1.00 moles of CH4 occupy at standard temperature and pressure? Now, guys, as you're thinking about the test, we will give you PIVITI, PF, TFV. We'll give you that equation. We'll give you PivNert. We'll give you the value for R. And we'll give you the value for standard temperature and pressure. You have to memorize nothing for this test. Okay, so guys, with that said, how are we going to solve this equation? Well, we're going to write down PivNert. If you'd like an example, certainly it's a good idea to do this with me. Now, guys, all you got to do is start on the left, work to the right, and when you find something you don't have a value for, call it X. So do we know P, which is pressure? Well, yeah, it's standard pressure. You don't have to memorize it, but it's 101.3 kilopascals. Now, guys, after that, we run into V, which is volume. Do we know the volume? Nothing's given in liters, but the first 2 words are what volume, which would tell us that volume is our X. So guys, as soon as we've identified our X, that means we've got to be given everything else. So N is number of moles. That would be 1.00 moles. R is the universal gas constant, which is 8.31 liter kilopascals per mole Kelvin. And by the way, guys, I shouldn't do this, but I'm going to. You don't have to put units on your numbers. But I'm going to this time to show you why these units work. And then, guys, temperature is standard temperature, which is 273. All right, so guys, grab your calculators. Let's make sure you can solve this thing. So before we do, let's talk significant digits. You ready? We've got 4, we've got 3, we've got 3, and we've got 3. So we get 3 significant digits in our answer. To solve this, you're going to go 1 times 8.31, that doesn't change anything, times 273, divided by 101.3. And when you do all that math, you find that the volume of 1.00 moles of CH4 at standard temperature and pressure. Plug in the numbers, do the math. What answer do you get? You already knew the answer. See, guys, back when you learned about the mole, you learned that the volume of a mole of gas at standard temperature and pressure is 22.4 liters. This is where we get that from. Huh? But now, guys, let me give away to you one of the questions that's going to be on the test next week. What if we did this problem over, and what if we said, okay, instead of doing CH4, what if we changed it to carbon dioxide? Same answer. Guys, that's the magic of Avogadro's principle. It doesn't matter what the gas is. Pivnert describes them all. Whether it's small molecules or big molecules does not matter. Pivnert always works. So guys, it does not matter what the identity of the gas is. So when you get that question wrong on the test, remember this moment when I just gave you one of the questions on the test. Okay, so guys, you good with the math? Is that all right? Okay, so there's one little curveball I need to throw you, and then I'm going to get out of your way and let you do your homework. Whether you choose to write this down or not is up to you, but it says this. A small rigid container contains 250 milliliters of helium at room temperature and a pressure of 85 kPa. What's the mass of the gas? This one's a little trickier. You may want to write this down. At least you certainly want to write down the answer. You can always come back and find the question by printing the notes. But guys, this one's, well, it's not. You just got to be careful. So let me give you a second if you want to write it down, and then we'll solve it together. So it says you've got a rigid container, a metal canister, if you will. And it's 1/4 of a liter, so it's about the size of a pop can. And it's full of helium. And the helium's at room temperature, and its pressure is 85 kilopascals, which is below standard. That's probably, well, here, we can look. Pressure in Utah right now. Oh. Oh, you know what? I've got to go back and change it. This is in inches. Oh, wait, I can get it on my phone. Well, it doesn't matter. Okay. So 85, it's probably about the pressure here. It's about 85 kPa. Well, here, I can check on. You guys know that your phones have barometers in them, right? That's how your phone measures altitude. And you can buy apps that can tap into the barometer on your phone and give you pressure. So, oh my gosh. The pressure here is 85.357 kPa. That's pretty cool. That's not bad. All right. So guys, there you have it. So basically what we're saying is you got a pop can full of helium, because it's probably 22 Celsius, it is 85 kPa, and I mean, this is us. So what does a pop can full of helium weigh? Right here. So we're going to find that out. So, Pivnert. So now, guys, we've got a problem. Reading the last sentence in this question, what are we solving for? Mass. But guys, mass ain't a part of Pivnert. It's not Pivmert, it's Pivnert. There is no mass variable in Pivnert. So what are we going to do to get mass? Good. Solve for moles and then convert to grams. So we understand that if we're solving for a mass, what we're really doing is solving for moles, and then we can easily convert. So we need a pressure, and our pressure P is 85 kilopascals. Now guys, go slow. We need a volume, but it's not 250 milliliters, 0.2500 liters. You've got to convert to liters by dividing by 1,000, and don't forget significant digits. Then guys, we've identified that N, our number of moles, for right now is our goal. It's not really our goal, but we can convert it to grams later. R, as we know, is 8.31. And again, if you don't put units on your numbers, that's fine. And then guys, temperature, be careful. It's not 22. Add 273. It's 295. And really, no, that's actually right, 295. So now guys, how do we solve this for x? Well, we take 85, we multiply it by 0.25, we divide it by 8.31, we divide it by 295. Looks like we get two significant digits because of the 85, and so I get 0.0087 moles of helium. But now, gang, we ain't done. Now we've got to convert this to moles. So this becomes a secondary calculation, a little bit of dimensional analysis. We bring this number of moles down, 0.0087 moles. It's a one-step dimensional analysis problem. Moles of helium go on the bottom. The mass of helium, which I think rounds to 4. Oh, it's over there. Yep. So two significant digits. It's 1 mole is 4.0 grams. Do the math, and it's 0.035 grams of helium. Gang, that's it. What do you think? Y'all okay? Okay, so yeah, as advertised, like 45 minutes. So guys, kind of a nice way to end the year, right? So you now have time to get your homework done, so you won't have homework over the weekend. You can get your labs written up and turned in. I'll get rulers and set those out for you. If you weren't here last time and haven't had a chance to print the lab makeup yet, I'm happy to do that for you. So guys, let's use today as a day to sort of wrap up some loose ends. Then when I see you on Tuesday, we'll do a lab. When I see you on Thursday, we'll do another lab. And then the test will be the following Monday. So guys, dig in, enjoy.